we're doing some really cool research on using approximation techniques to reduce the cost of data analytics. So let's get right into it. All right, pop quiz for you. So there's like 2 graphs here showing the result of a SQL query that's run over time over different data sets. Raise your hand if you can spot a difference between them. Oh, okay. Nice one. Okay, apart from red and green. All right, so one of these is something that you would generate with exact analytics, right? You send a SQL query to a database and you get the result, you plot it. And one of these is generated by our system, SketchDB, with very, very high accuracy. Now let's say this graph is part of a dashboard. You want to generate a graph like this, let's say once every second for an hour. This is what the workload costs for that look like, right? So SketchDB is able to produce a virtually indistinguishable result with 1/10 of the cost. Let me tell you how we do that. So this is what the big data stacks today look like, right? So you have raw data coming in. You have a messaging layer like Kafka, Red Panda, et cetera, et cetera. And this will then send the data to a stream processing layer. You have Flink, Spark, Kafka Stream. There's multiple of those frameworks. You do some stream processing on that data, transform it, maybe pre-aggregate it, and then send it to a database where it's stored, right? And then again, you have multiple choices of databases over there. And then this big data stack will serve different kinds of workloads, right? So you could have an observability workload to monitor your systems. You could have AI machine learning workloads, which are going to send queries to your database, get the results back, and then use it for downstream visualization, analysis, and so on. Now, it's no secret to the people in this room that the cost of this is increasing, right? So there's increasing volume and complexity of the data that you're ingesting, and there's increasing volume and complexity of the workloads that you're trying to run on top of this big data stack. And that's leading to more cost, more power usage, and just higher latency, right? You're paying more and you're waiting more. It doesn't sound like a good trade-off space to be in. And so you could actually think about having your traditional system optimizations, right? I could have a faster stream processing layer. I could have a faster database. Maybe I can write better SQL. But all of these traditional system optimizations, while useful, are not going to take you very far, right? What you need is a fundamental shift in the way you actually think about big data stacks. You need a quantum leap of improvement, and this is what SketchDB is trying to do here, right? So show of hands, how many people have heard of sketches or sketching algorithms, maybe HLL, Bloom filter? Okay, perfect, awesome. So quick refresher, sketching are these like cool mathematical building blocks. They're algorithms that operate on top of streaming data, and they're going to calculate some aggregate statistic on top of that streaming data. But the cool thing about them is that they are designed to do this in an approximate manner, right? So instead of having a result that's 100% accurate, it can still be high accuracy, maybe 98%, 99%, but it will be approximate. And the benefit of that is you can do this calculation with orders of magnitude lower resource usage, right? Your memory will be lower, your CPU cycles spent will be lower, and that just leads to a lower downstream cost. So there's a bunch of literature in the theoretical computer science space about different sketch algorithms that have been proposed for calculating different aggregate statistics on top of streaming data. Now, the people in the room who are familiar with sketches might be thinking that, hey, there's already some sketch implementations that are out there in databases, right? So for instance, I know ClickHouse and Druid have it. I'm sure a lot of other databases have it too. So there are these HLL implementations which can actually count, do a count distinct on a column, right? So if you have a column and you want to count the number of distinct elements, you have a sketch implementation for that. There's also an open source library called Apache Data Sketches, which has these open source Java implementations of sketches, which can integrate with a couple of databases. Now, while this is useful, I would argue that sketches have been underutilized, right? These solutions are point solutions to point problems, right? So problem was, hey, I want a faster cardinality query or faster count distinct. All right, I'll go and implement an HLL. My problem was I don't have these open source sketch implementations. All right, we'll go and build Apache Data Sketches. So while they've been useful, they only satisfy a very niche subset of queries, right? If I have a select count distinct, or if I want to do a percentile on top of a column, I can do that with sketches, not much else. And in using these sketches, the cognitive burden is on the user, right? So the user, that is the query writer in this case, has to decide which column can I use a sketch on, which sketch algorithm should I use, how do I configure the parameters of this algorithm, right? And that kind of goes against the whole principle of a declarative query language, where you specify your high-level intent and the system does everything that it needs to do to kind of get that answer, right? So in the current system that we have, that's not being satisfied. And then a lot of these are simply painful to deploy, right? So data sketches, for instance, has like some integrations with Druid, Pinot, maybe a couple of other, but now let's say I want to bring ClickHouse. It's not very easy to use this. So this is the kind of problem that my PhD research is trying to tackle, right? So I'm trying to build a big data stack that is sketch first, right? Or treats these sketches as first-class citizens and is able to optimize around them, right? So instead of supporting only a niche subset of queries, we have a diverse query workload that we've been able to support with sketches. And the great thing about this is that instead of placing the cognitive burden on the user, we are completely transparent to the user. So the user sends their SQL query as it is, and internally we are able to map that query to different kind of sketch or compositions of sketches, and able to answer that without asking the user to actually decide, hey, this is the exact sketch that I want to use on this column with these parameters. And in the process, we've also made it extremely easy to deploy and work with existing systems. So this is a quick preview into how SketchDB democratizes sketches, right? So this is back to our big data stack. So SketchDB has this streaming compute layer, which attaches to the existing stream processing layer that you would have, like Flink, for instance. And as the data is being ingested, it computes sketches on top of them and sends it to the SketchDB query engine. So the SketchDB query engine is a separate box that we have built. It's a research prototype right now. And this query engine sits between the user and the existing database that you have, right? So let's say you have a dashboard workload. This is generating an OLAP query that would normally go to the OLAP database. So we intercept that query and try to use the computed sketches to try and answer that query. And in the common case, we're able to answer it, quickly send back an accurate result. But if we're not able to answer a query, then you just send the query to the OLAP database as before, right? So you're no worse off than before. And in doing this, like, the aim is not to support each and every query, but support the 80%, the common case, which you can optimize, and then the rest 20%, you already have your database there. So this is what our initial design of SketchDB is. And there's several research enablers in actually making this possible. This is like the research that we're doing at Carnegie Mellon. So a couple of the things that we have done is for diverse queries or diverse SQL queries, we've actually been able to compose different sketches together. So instead of just supporting a simple cardinality or a simple percentile query, we can actually support more complicated queries with where clauses, with different, like where clauses that are on spatial conditions like metadata, where clauses on the time interval, and even things like Druid stop and queries, which kind of compose different columns together and sort them by some aggregation function. To make it transparent to the user, we've developed a system called SketchPlan, which takes an existing query workload and automatically decides what sketch algorithms should be deployed to answer those queries, what configuration they should have, and so on, right? So we've automated that task and made it transparent to the user. And we've also adopted like a drop-in DB agnostic middle box architecture, right? So instead of existing solutions which are like tightly coupled with a database implementation, we have a separate query engine which can sit in front of your database and transparently accelerate your queries. So this is still very much active research that we're doing, and we're actually hoping to have an open source release for this soon in the next couple of months. So quick takeaways: big data cost is increasing. You can do traditional system optimizations, and you should, but you actually need a quantum leap of improvement, and you need to shift left, to use the words that people have been using, to actually improve the cost or reduce the cost by an order of magnitude. And this is exactly what we're trying to do. Come talk to me about your use cases. I'm very interested to learn more. if you think this would be useful for you, if you think this would be terrible for you. I would love to hear both sides of it. That's all that I have. Thank you so much.